Landscapes are dynamic tableaus, maybe not in the human lifetime, but over geologic time, they age just like us. With a careful eye, one can discern the relative age of these landscapes and get a sense of what processes have been acting on it. Compare these two areas, one which formed relatively recently and one which formed hundreds of millions of years ago and has been evolving ever since. The first one has high elevation, jagged peaks with steep valleys. This area is a result of recent geologic mountain building processes such as tectonics and volcanism. It's a relatively young landscape. Image number 2, on the other hand, is dominated by gently sloping low elevation hills. This is a much older landscape that's undergone weathering, erosion, and mass wasting. The landscape has become low enough so as not to have much potential energy, and these superficial processes have begun to cease. Mass wasting is one of these processes that serve to flatten landscapes by the downslope movement of rock and soil under the influence of gravity. Let's look at some images of this happening. Okay, now are you excited to learn about landslides? In our discussion of mass wasting today, I want to cover what is mass wasting? How does it work? What are the mechanics behind it? And in particular, what drives mass wasting and what are the forces that resist downslope movement? Then I want to cover what are the factors that determine slope stability? And then how do you classify different mass wasting events? And then finally, I want to finish with can we prevent them and how do we mitigate the damage? Just some basics at first. We often see these events referred to as landslides, but a more general and appropriate term would be mass wasting. A landslide is a very specific term that refers to a specific type of event, but a more general term is mass wasting. It's more inclusive in general. And remember from our earlier video, erosion is not the same thing as mass wasting. Erosion requires mobile agents such as water, wind, and ice. Sediment is transported by these movements. But mass wasting, on the other hand, is the transfer of rock or unconsolidated material downslope, but due to gravity, and the movement of the material does not require a mobile agent. Water does contribute to mass wasting in the sense that it reduces the strength of materials, but it's not directly involved. And also note that mass wasting is not a type of weathering, but there is a connection since weathering reduces the strengths of rocks, which then makes them susceptible to mass wasting. It's tempting to say that only unstable slopes fail, but really slopes are constantly changing and being altered by geologic processes. Therefore, slopes are always geologically unstable because slopes change over time and space. And a bit of vocabulary before we start. The word colluvium refers to earth material, so rock and sediment and soil that's been moved by gravity, as opposed to the word alluvium, which we talked about in an earlier video, which refers to earth materials that have been moved by water. We mentioned in the beginning that higher elevations are more susceptible to mass wasting. Why is that the case? Since the movement of rock and soil is due to gravity, why are higher elevations more susceptible to this? Well, it's because they have more potential energy, which gets converted to kinetic energy. Look at the equation for potential energy. Potential energy equals the mass of the material times acceleration due to gravity, which is a constant 9.8 meters per second. And the third variable is the height or the relief of the slope. Therefore, a unit mass potential energy is proportional to its height or relief. So elevation does matter. There are a number of forces acting upon a hillside that can be broken into two opposing groups. One is the driving forces, which act to move the material downslope, and the other are the resisting forces that oppose that downward movement. When the resisting forces holding the rock in place are overcome by the driving forces, a hillside fails. This generally happens when the resisting forces are reduced due to water pressure. So in general, the driving forces are gravity, the weight of the earth materials, the weight of water that sometimes is involved, and the weight of structures that possibly are put on slopes like buildings. And the resisting forces are basically the materials and their strength, their cohesion, and the internal friction of the material. So the first place we want to begin when talking about these sort of mass wasting events is to look at the factors that affect slope stability. They include the amount of water, whether the slope has been oversteepened, whether it has vegetation. And as we'll see, there are often other events that can trigger a failure, such as an earthquake, a volcano, or a hurricane. Let's start with the slope angle of a hillside. All earth materials have an angle at which the material is stable. It depends on what the earth material is made out of: solid rock, sand, silt, clay. And the maximum angle that material will hold without failure is called its angle of repose. Sand has an angle of repose of about 33 degrees, whereas a bedrock cliff may have an angle of repose of nearly 90 degrees. And the angle of repose is measured relative from the horizontal. At that angle, the base and the height of the pile of the sediment can continue to increase, but the angle of the sides will remain the same. If that angle is increased, the slope will become unstable and material will slide down slope in an attempt to regain that angle of repose. So how do you get a slope that is steeper than its angle of repose? Well, human forces can cause that, or natural forces can make that happen. Either way, the hillside will become unstable, and a small change then can trigger a landslide, such as rain. Kind of like an avalanche, a snowpack can remain stable, that is, until someone skis across it, creating vibrations or just a little bit of added weight. So before the avalanche, you could say the slope was metastable until the conditions slightly changed. Something we have not yet covered is water, and what role does that have in the process? But there's an interesting note about water. If we add a little water to sand, the angle of repose will increase, possibly to 60 degrees or maybe even 90 degrees, such as when you're building a sandcastle. But if too much water is added, the pore spaces of the sand will fill and the grains become further apart, and it will decrease their shear strength, and it will lower their angle of repose, and the sandcastle collapse. This is because a little bit of water increases the cohesion of the sand, but too much water will decrease the friction between the grains. So there are many different scenarios in which you can imagine when a hillside would become oversteepened. Maybe a road is being constructed that may necessitate cutting into a hillside, or maybe an expanding area, let's say, to build a house. Or it can happen naturally as a landslide removes material which leaves the remaining area oversteepened. Or think about a coastal area when waves have removed the base of a cliff and undercut it. All these scenarios would create an oversteepened slope and make it less stable. So let's look into why oversteepening the slope leads to instability. The force of gravity can be resolved into two different forces. One force that is parallel to the slope and one that is normal to the slope. The one that is normal to the slope adds to hold the material on the slope, whereas the parallel force acts to pull the material down. So imagine what would happen to the relative magnitude of these stresses as the slope angle is increased. The force parallel to the slope increases and may become greater than the normal force which holds it in place, and the hillside will slide. And when a slope is at its angle of repose, these forces are in equilibrium, but with an increased angle, the parallel forces become stronger. Two hillsides with similar slope angles may not respond in the same way. In fact, it may seem curious to see some relatively low-angle hillsides with evidence of sliding. Why is that so? Well, one of the major variables that determines slope stability is the underlying geology. In general, stronger materials hold steeper angles, such as crystalline rock, maybe granite. Less strong rocks, such as layered sedimentary rocks, and the most unstable are heavily weathered rocks and unconsolidated sediment, which have very little strength and cannot hold a very high angle. You only have to look at the profile of the Grand Canyon and you could see that some rocks hold a vertical cliffs and others that are weaker, such as shales, have undergone mass wasting and have a much more gentle angle. Not only is the inherent strength of the rock important, but it's also its orientation, the alignment of any planes of weakness, such as bedding planes within a sedimentary rock, or foliation, which is how the grains are aligned in metamorphic rocks, or simply fractures. These all impact the stability of a hillside. If the direction of the plane of weakness is roughly parallel to the surface, it makes the area more unstable. In other words, if a rock tilts or dips in the same direction as the slope, it is inherently less stable. And as I mentioned, water is almost always indirectly involved with mass movements, but not in the way you're possibly imagining it is. Water does not directly carry the earth materials downslope, meaning it's not the movement of the water that causes the slide. It's gravity, but the majority of the time, water is involved in some way. There are certain cases, such as rock falls, where water is not involved, but most are. Water's role has a number of different components to it. First off, water lubricates surfaces, which decrease their strength by lubricating the sliding layers. Secondly, the water can fill pore spaces within rock or sediment, and that destroys the particles' cohesion. And this can disaggregate unconsolidated layers. Water also reduces the internal resistance or friction, which is a resisting force. And then lastly, it can add mass to an area, which makes it more susceptible to sliding. So if water is such an integral part of slopes failure, it's not difficult to understand why an area with poor drainage would be less stable. And many mitigation strategies involve artificially draining a poorly drained area to make it safer. Another factor affecting slope stability is the role of vegetation. Plants have a number of roles, including absorbing water, which reduces runoff during rain. Secondly, the roots stabilize the soil. And then thirdly, evapotranspiration by plants removes even more moisture. So hillsides that have foliage are much more stable. And along those same lines, one of the triggers for landslides can be recent forest fires that remove that anchoring vegetation. It's very typical after summer forest fires the following winter that these denuded slopes then becomes much more susceptible. Another common trigger are earthquakes. Sometimes vibrations from earthquake is enough to dislodge a metastable slope. And furthermore, the ground shaking can also cause liquefaction, which is when water-saturated material begins to flow like a liquid. A famous example of this occurred in 1970 in Peru, when a magnitude 7.7 earthquake destabilized a northern wall of Mount Huascaran, causing a rock, snow, and ice avalanche which buried an entire town and its 18,000 residents during an Italy-Brazil FIFA World Cup game. The landslide was so powerful that it jumped a 200-meter ridge as it flowed downslope. And the avalanche was about 3,000 feet wide and about 1 mile long, and it advanced about 10 miles downslope at speeds greater than 186 miles per hour. There are a dizzying number of classification schemes for mass wasting, and we won't cover them in detail, but I'll review a few of the variables that go into deciding what to call these slope failures. The most important characteristic of most of these classification systems is how that material moves. The second criteria is what type of material is being transported. Is it solid rock, unconsolidated sediment? And if sediment, what's the dominant grain size? And some classification systems address the amount of water that's involved in the process. I want to discuss at least the ways the material moves downslope, since that's an integral part of most classification systems. There's 4 main mechanisms: a fall, a slump or slide, a flow, or creep. Keep in mind, some of these processes are super fast, like falls, occurring in less than a minute, while some are excruciatingly slow and barely perceptible. The first and easiest type of movement to understand is a fall, which is when blocks of bedrock release from a steep rock face and free fall. Little or no shear displacement take place. Falls are strongly influenced by gravity, mechanical weathering, and the presence of interstitial water. These rocks form talus at the base of the slope, which is a pile of accumulated rocky debris that forms at the base. These type of falls are common where there are lines of weakness in an outcrop, such as a well-jointed rock, or maybe fractures in the parent rock, or maybe along bedding planes. Think of rock falls in Yosemite. Based on what you know about the mechanical weathering process of exfoliation, an amazing example of a rock fall occurred in Yosemite July 10th, 1996, when about 80,000 tons of rock fell from the cliffs above Happy Isles in Yosemite and landed at a speed of over 240 miles per hour. This impact of this rock generated seismic waves about 120 miles away. The second type of movement are either slides or slumps, and that's basically the rapid movement of large blocks of detached material that slides more or less as a unit. So there's very little internal movement in the block, and it moves along a well-defined surface. So this can occur in oversteepened slopes and commonly in clay-rich materials saturated with water. These failures are about 10 times longer than they are wide. So slides and slumps are very similar. The only difference is the shape of the detachment surface. If the slope or the detachment surface is planar, then it's a slide, and if the surface is curved, then it's a slump. One of the more dramatic and infamous slump is the one at La Conchita, which is between Ventura and Santa Barbara in California. The event in 2005 killed about 10 people and destroyed dozens of homes. And it was actually a remobilization of a 1995 landslide. The bluff above this area has a slope of approximately 35 degrees and consists of really poorly cemented marine sediments. And it was after a year in 1994-1995 winter that had twice the normal amount of rain. And then again when it slid in 2005, it was the end of a 15-day period of near record rainfall events. The third type of movement are flows, and these are really rapid type of events involving flow of soil and or rock or mud and that contain a lot of water. So material moves downslope as a viscous liquid. It's not a coherent block like a slide or a slump. And because of these fluid properties, these flows follow canyons and streams. And they can be identified by their kind of hourglass shape. So the material liquefies and runs out, forming a bowl or kind of a depression at the head. The fourth and kind of an unusual type of movement is called creep. As its name implies, it is slow. Soil or rock creep is accompanied by repeated expansion and contraction of soil due to wetting and drying or freezing and thawing. And this causes a net downslope migration of particles. The surface layer of the sediment moves downslope faster than the deeper layers. And for this reason, creep will cause downslope tilting of anything such as trees or posts or monuments or anything that's been embedded in the soil. This type of movement is seasonal, so it happens when there's a lot of rain in the winter or when it's freezing and thawing. And it's a really slow, almost imperceptible, continuous type of motion. It's fun to cruise around the Bay Area and look at hillsides to see if you can spot where sliding has happened. And a few things to look out for are scarps. That's the upper part of the slide where vegetation has been stripped away or a general lack of vegetation in a specific area. Or maybe there are tilted trees or fences. Or maybe the topography is really hummocky or kind of lobate. These are all signs that a landslide may have occurred in this area. Hazard mapping is the most practical way to mitigate damage from slope failures. Engineers understand the forces behind the failures and the geologic situations where they're likely. So the first question is, why are we still building or rebuilding in those areas? Good question, but we are. Although the simplest means of dealing with landslide hazards is to avoid construction on steep slopes and existing landslides. But this isn't always practical. So what are some of the techniques that engineers use? Well, the first is real simple: vegetation. Planting vegetation is particularly effective in stabilizing slopes that consist of sediment. The roots bind the material and can penetrate into the underlying rock to anchor the sediment. So vegetation with deep roots is most effective. Secondly, retaining walls, which are structures to support a soil mass permanently. They're designed to prevent sloughing of loose material onto roads or other structures. They can be made from timber, steel, plastic mesh, reinforced earth, even spray on concrete called shotcrete can be used. Keep in mind, these walls cannot be used to stop landslides from occurring. It just keeps the debris from encroaching on a road or whatever structure it is that they're protecting. And they cannot protect from large failures. Just look at Highway 1 and the number of days it's been closed over the last few years. The third technique involves diverting water away from the hillside. So draining the groundwater away from the area to reduce the potential for a rise in groundwater levels. Another rather coarse approach, but related to this, can be to place an impermeable membrane, such as a tarp, over the hillside, which can inhibit infiltration. And then finally, a very expensive technique, but rock bolting, which includes bolting or anchoring to fix hazardous blocks in position and prevent movement. So the last thought I want to leave you with is that slope failures are natural as well as human-induced hazards that will continue to happen, especially here in California, where we have most of our yearly rainfall over about 4-month period. And this creates drainage issues. And furthermore, most of our beautiful state is crisscrossed with faults that fracture and weaken bedrock, creating another risk factor. So our best bet is to map these hazardous areas and not build into them. Listen to geologists, not developers.